Well, all right, so let's pick up on this. Ecologists have been thinking about this for a long time. It's been a classical question, and there are many, many hypotheses that have been produced. In fact, if you go to good old Wikipedia, you can find a bunch of them. Some of them have to do with how much space there is or the geographic distribution of habitats. Some of them have to do with the fact that the conditions for energy supply are different in the tropics and the poles, and the climates are different. Some of them have to do with history and the accumulation of evolutionary events. And there are also a bunch of biological hypotheses as well. And you can go into Wikipedia and read about all of these. We're going to take a look at just 3 of them and try to see if we can sort them out, make some sense of them, and test them. These 3 we're going to work on are the mid-domain effect, the climate harshness hypothesis, and a hypothesis related to effective evolutionary time. All right, so let's start with the climate harshness hypothesis, right? Because the poles are nasty. It's difficult to live. It's cold all the time. It's freezing. In the tropics, it's warm and wonderful, and maybe that helps things out for species to coexist with each other. So the climate harshness hypothesis goes something like this. This latitudinal diversity gradient may exist simply because fewer species can tolerate the conditions at higher latitudes. And at low latitudes are more amenable to living things, and therefore more species can live there. So think about that for a while. It makes a certain amount of sense, doesn't it, right? It does make some sense on the surface. We know that species distributions are often subject to physical tolerances of particular species. For example, right? Fish don't live on land. So why are there no fish on land? Well, because the fish can't live there. Right? So that's a pretty simple explanation. Here's a more subtle explanation for the Arizona desert that we live in. What controls the distribution of saguaro cactus? And that's the distribution shown here in green in this map. And it turns out that the northerly or the upper elevation regulation border of the saguaro cactus is very closely aligned with the probability for consecutive days of frost. Because the cactus is a species of the desert, very intolerant of frost. And so we can see very nicely that the geographic distribution of this particular species is heavily controlled by the environment and the possibility of freezing temperatures. But if you think about it, though, this hypothesis is a little bit circular because it says something like this. Well, there aren't many species in polar regions because there aren't very many species that can live there. Right? It's kind of a circular argument, and that's a problem. But also, right, if you think about it as well, right, there are many species that can live in polar conditions that aren't actually found in particular polar regions, right? So there are many more species that can live in the polar zones that are found in particular polar zones. So there must be something else going on. What's an example of that? Think of the most famous polar animals that you can think that are out there. What are they? Penguins, right? And polar bears, right? How are they distributed? Well, despite what the Coca-Cola company tells you, there are no penguins in the Arctic and there are no polar bears in the Antarctic. So the distribution maps are shown here, right? So the polar bears are in the north and the penguins are in the south. Well, if you took a population of penguins and put them in the north, they probably could make a living. Similarly, there are seals to eat in the south, and polar bears could probably get by down there. So they don't live there just because they happen to never have gotten there. So this explanation of climate harshness is perhaps not the full explanation, and one suggests we need to go further than that. All right, so I don't know. Climate harshness hypothesis, I think we should leave that out for the time. It's not a very good, very deep explanation for the patterns we see in diversity in different ecological communities. All right, so let's take another one of these hypotheses on. This one's called the mid-domain effect. It has to do with the distribution of species and their ranges. And if you think about it, right, the Earth is only so large, right? And so we can imagine looking across the poles through the equator and make the argument like this. Well, if species latitudinal ranges were randomly shuffled across the geometric constraints of this bounded area of the Earth's surface, right, species ranges would tend to overlap more toward the middle of the domain than toward the end, right? And therefore, you would tend to see a peak of species abundance in the middle latitude areas. Let me illustrate. So I'm going to throw a bunch of species ranges up, sort of randomly across the whole north-south axis of the Earth. right? And you can see, right, the big ones have to overlap the equator because have a pretty wide extent, and the small ones go everywhere. But if you just throw them up there like that, you can see, right, and to count, you can make a transect across at individual latitudes, and let's do that, and count every species we see at each latitude. And when you do that, oh, well, lo and behold, there's more species present around the equator in the middle latitudes than we see toward the poles, just because of how species ranges would have to sort out just by geometric constraints. And so the mid-domain effect does seem like a pretty reasonable hypothesis. But not everyone is convinced of that, right? And if you think about the amazing and incredible diversity that's out there in the tropics, this can't be the whole story, right? There must be something more to it than that. And if you think about it for a while, maybe this came up in your hypotheses as you were thinking about it yourself, right? The tropics have really long evolutionary timescales, right? They are stable for thousands and thousands and millions of years. Whereas in the temperate zone, the glaciers are coming and going back and forth over timescales of 20,000, 30,000, 50,000 years, wiping everything out, receding, right? And so you would think that that would matter in how much diversity a given area could support. And in fact, that's what is caught up in one of the hypotheses called the effective evolutionary time hypothesis. This argument says that diversity at a given latitude is determined by the evolutionary time under which the ecosystems there have existed under relatively unchanged conditions, and by the evolutionary speed that is determined by the effects of environmental conditions, especially temperature, right? Things tend to go faster when they're warmer. That would include perhaps the rate of speciation and the production of new species. And so basically the argument here is that diversity at any given time in a given place is the balance between the production of new species and the extinction of species. Now later in the semester we'll talk about this idea of speciation, so we're not going to go into it now, but you can imagine that there's a process by which new species are generated, and here it's proposing that perhaps that process itself is temperature dependent and may go more rapidly in tropical areas. So let's just illustrate what this means so we get our axis again here about the different parts of the globe. The argument here is that in the equator and equatorial regions, the rate of speciation is greater than the rate of extinction. So you accumulate species in those communities. On the other hand, the argument here is that extinction rates are higher in the polar regions, while speciation rates are lower, and therefore they tend to accumulate fewer species over time. So how can we test this? It's a pretty hard one to test, right? One way we could test it would be to estimate speciation rates at different latitudes or different temperatures. And the prediction would be, if this hypothesis is true, that the speciation rate will be higher in warmer latitudes than in cooler ones. All right, so I'm going to show you a test of this done by some colleagues that I know. There they used fossil data to test this hypothesis. They went into the fossil record with these things called foraminifera and used them to quantify speciation rates of this form of life in different latitudes of the Earth, using these things to then evaluate how the speciation rate varies with temperature in the equator versus the poles. So what's the prediction if this hypothesis is true? What should this relationship look like? Maybe you can make a graph in your head.